Hi everyone. So this is the first part of lesson 3.8, our last lesson in unit 3 on applications of the derivative. So hopefully you have the handout that accompanies this lesson, and I thought maybe we could get through the first 3 problems and then you'll just have a couple to try on your own. So hopefully by now you've watched the 4 videos I asked you to watch, and that should give you some kind of context, some background as we get started on trying these on our own. So the calculus that's going to be involved, you'll have 3 different options as to how you want to solve these problems in the end using the calculus. One of those is the extreme value theorem, so I thought it might be good to review that a little bit. We did that back in lesson 3.2 at the very beginning of unit 3. This would have been before Christmas. And what the extreme value theorem tells us is that if we have a continuous function on a closed interval, that we are guaranteed both a maximum and a minimum to occur on that interval. So what we're going to be doing is now applying this to application problems in which we're trying to find an absolute extremum, either a maximum or a minimum. Then there's tons of applications of this in the real world, whether it's manufacturing when you're trying to minimize cost or maximize profit, in science when you're trying to figure out when the number of bacteria in a population is going to be at a maximum or even at a minimum. There's lots and lots and lots of applications, as you'll come to see pretty quickly. So in terms of some tips for solving, and these are on your handout as well. If we can draw a picture, we will. You know I'm a big fan of that. You're going to notice the layout is pretty similar and systematic as it was when we did related rates. Remember, we had very much a set way we worked through all these problems. You're going to find the same with this. Once we have our diagram drawn, we want to establish what it is we're trying to maximize or minimize and write an equation to reflect that. So if we're trying to maximize volume, we need a volume equation. If you're trying to minimize cost, we're going to need a cost equation. And typically you'll hear this equation that reflects what you're trying to maximize or minimize. You'll hear that referred to as the primary equation. A lot of textbooks refer it to that way. Now you do want that primary equation to be in terms of a single variable. If it's not, you need a secondary equation that you will be able to write and use to get that primary equation down to a single variable. And then once you have your equation written, that's when the calculus kicks in, and you're going to find that maximum or minimum either by using the extreme value theorem, the first derivative test, which we'll call for a number line, or the second derivative test. And we'll be looking at examples of using all of these. You might find in the end, once you get familiar with these, that you'll gravitate to one or the other, and that's fine. You'll typically will not be told what way you have to solve it. It's good if you can be a little flexible and know how to work with all of them. Sometimes one will be easier than another, depending upon the equation. Now, one thing to remember though is if that you're going to use the extreme value theorem, you do need to have a closed interval as the domain, and a lot of times that's what's going to prevent you from using the extreme value theorem, because you won't have a closed interval. But if the chance arises that you do, remember you're going to need to find that absolute maximum or minimum by locating the critical numbers and also considering the endpoints of the interval. So I know we'll be looking at one of those somewhere along the line. If you don't have a closed interval, then you'll be using the first or the second derivative test for relative extrema. And it's the first derivative test that we'll do a number line analysis for. So, first problem. If any of you sat through any of our enrichments that we do here at NCSSM when you were in middle school, perhaps you remember the box problem, and that's exactly what this is. So what we're trying to do is create an open box from a rectangular piece of sheet metal that measures 20 inches by 32 inches. And the way we're going to do that is by cutting out squares from each corner and then folding up the sides. Feel free to grab a piece of paper and try it yourself. Depending upon how big that square is that you cut out, that's really what, that determines if you have like a really short, squat box or if your box is really, really tall. And hence, it's going to affect the volume. And what you're trying to figure out is the maximum volume that it can be achieved. So let's go ahead and draw a picture of what this thing would look like. So let's say this is the side that's 20, and this is the one that's 32. And remember, what we want to do is cut out squares from the corners. So ideally, those squares should all be the same size. And that's the part we don't know, is how big the square is that we're going to cut out. So our variable x is going to represent the length of the side of the square that we're going to cut out. So in this case, if you take a look at step 2, next thing we want to do is establish what it is we're trying to maximize or minimize. And in this case, we're trying to maximize volume. And we all know how to get volume of a box. It's just going to be length times width times height. But we do need to put it in terms of these variables. All right, so let's start with the length. Well, the length, let's call the side that's 32. Let's refer to that as the length. Now remember, you're cutting out these squares on the ends. So really the only part that remains for the box is that part right there. So that length can be given by 32 minus 2x. All right, now the width is going to be this little part right here. So that's going to be 20 minus 2x. Now the height, if you can picture it, the height of the box is being dictated by the size of the square that you cut out, which is x. So the height in this case is simply given by x. So this is what we would refer to as our primary equation. It's the equation that reflects what it is, in this case, that we're trying to maximize. Notice it is all in terms of one variable. So we're good to go there. All right, so we do not have a need for a secondary equation. All right, so I took the liberty of going ahead and multiplying this out already. When you do that, you get 4x cubed minus 104x squared plus 640x. Feel free to check it if you wish. Now let's talk a little bit about the domain, because we mentioned that if we were to want to use the extreme value theorem, we need to make sure we have a closed interval for the domain. So in this case, the domain is going to be the allowable set of x's. So remember what x represents. It's the side of the square that we're cutting out. Well, we can't cut out a negative length, so we know it can't be negative. Technically, it can't be 0 because, well, then you're not cutting anything out. So it has to be bigger than 0. Now the question is there something that it can't go over either? All right, and because of that one side that's 20, and specifically the 20 minus 2x, we really can't go any higher than 10. Actually, we can't even equal 10 because then you really don't have a box either. So you can get really close to 10, but then you have a very teeny tiny base to your box. But because this is an open interval, we cannot use the extreme value theorem on this. So we're going to have to go with either the first derivative test or the second derivative test. Now both of those pretty much are the same up until a certain point. Both of those tests require that we find the derivative and then get our critical numbers. Okay, so let's do that part, and then we'll kind of break it off into see what the first derivative test solution would look like, and then the second derivative test. All right, so we need to find our derivative. So that's going to be 12x squared minus 208x plus 640. All right, so whether you're doing the first derivative test or second derivative, you need your derivative. We need our critical numbers. So remember how we find critical numbers is we have to set this derivative equal to 0. Now to solve this, you easily could use quadratic formula on your calculator. That's fine. If you wanted to factor it, there is a 4 that you could factor out, and then you can factor the remaining polynomial, the remaining quadratic. That would factor into 3x minus 40 times the quantity x minus 4. Feel free to give that a shot. So we get two answers for x. We get 40 over 3 and we get 4. And there are critical numbers. Now remember our domain though. We can't go higher than 10. 40 over 3 is bigger than 10. This one's no good. That's an extraneous solution. So x equals 4 is the only critical number. All right, so up to this point, no matter which way you choose to do it, you're going to have to do this. All right, now it depends upon, for the rest of it, whether you opt to go with the first derivative test or the second derivative test. All right, so let's pick it up from there. All right, so first derivative test. This is the one with the number line analysis. All right, so remember our critical number was 4. And just like we always did, we had to indicate that it was substituting into the derivative. Some people like to indicate the domain on there just to kind of make sure they keep in mind what numbers they can and can't use. So we'll first pick a number in between 0 and 4. And remember you're substituting into the derivative. Don't forget that. If you do that in this case, you get a positive answer. Then we're going to pick a number in between 4 and 10, substitute that into the first derivative, and we get a negative. So since our derivative is changing from positive to negative, indicating that the original function changes from increasing to decreasing, voila, we have a relative maximum. So what we would have in this case is the maximum volume occurs, I can't spell, when x equals 4, and what was that, inches, I think? And I think they wanted us to find what the actual maximum volume was, so you need to substitute the 4 into the original volume, the original, and that volume ends up being 1,152 cubic inches. All right, so that's what the first derivative test looks like. All right, let's do the second derivative test. So remember, everything would be the same up to that point. You would have had to find your first derivative, find your critical numbers. With the second derivative test, though, no number line. Remember what you're doing is taking the critical numbers from your first derivative and substituting them into your second derivative. So we do need to find the second derivative. So in this case, we end up with 24x minus 208. And we're going to substitute our critical number into there. So we get 24 times 4 minus 208. That gives us a negative 112. So remember what the second derivative test told us about. Second derivative overall, remember, tells us about concavity. So we know since at x equals 4, our second derivative is negative. Remember what that tells us. So v is concave down because the second derivative is negative when x equals 4. And remember our pictures, concave down looks like this. So that's why there's a relative maximum at 4. And then pretty much you'd have the same conclusion that we got before. As I mentioned earlier, hopefully you will become flexible at using either of these. The nice thing about the first derivative test, it always works. Always, 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 always. But if you have a pretty simple equation, this was just a polynomial. This one was pretty simple. And especially if the second derivative is really easy to find like it was here, sometimes the second derivative test is just as easy. So that's where I'm talking, if you can develop maybe a little bit of flexibility and, kind of don't pigeonhole yourself into always just doing one way, okay? That is my hope for you, okay? Now, that being said, no, I'm not going to tell you which way you have to do it. So it's up to you. Like I said, my hope for you is that you will develop a little bit of flexibility. All right, let's try another one. So now we're given a circle whose radius is 10 centimeters, and we want to make a cone out of this. Get a piece of paper, cut out a circle, mark on the circle where the center is. And the radius is 10. No, seriously, like get a piece of paper and cut out a circle, okay? Really, because then you'll see what this looks like. If I was there with you, I'd be doing this and showing you. I should have had my video going. So if you kind of pinch the, hold like the middle, you kind of want to like swirl it around and turn it into a cone. Okay, so like when you make a cone out of it, it looks like this, obviously. All right, now the question is, where did the 10 go? All right, so the 10, you might remember that being called the slant height of the cone. That's really where the 10 went. Okay, it's not like the actual radius anymore of the bottom. Okay, it's actually like the hypotenuse if you want, because what we're going to do is sort of think of this as like a right triangle in here. Like right here. All right, and notice how the 10 is sort of like the hypotenuse. Okay. So let's just start maybe let's call that X instead of R. I'm just going to call it X. And we can call this height H if you want, or Y, whatever you want to call it. So notice what we're trying to do is maximize the volume of the cone. All right, so we want to maximize volume again. All right, now you have to remember how to get volume of cone. Yes, that's one they would give you on the AP exam. But it is 1/3 pi r squared h. Now I didn't use r, I used x, so maybe we should put an x there. All right, so this is what we would refer to as our primary equation. But notice there's two different variables. Okay, so this is the case in which we would need a secondary equation so that we can rewrite this thing just in terms of a single variable. Think back to the related rate problems. Remember, you often had to do that with the cone problems? It's the same thing here. All right, remember before with the related rates, you would set up like a proportion and you would cross multiply, and that would enable you to get rid of one of the variables in that main equation. That's really what you're going to do here. All right, so the secondary equation we can write in this case, if you take a look at that little triangle I drew in there, think Pythagorean theorem. So we could do like x squared plus h squared. That becomes 100. We have to decide if we want to get rid of the h or the r, or x rather. Remember, this is an x. Well, I got x squared right here, and I got it right here, so maybe I could just do x squared equals 100 minus h squared, and then maybe put that right into there. Now everything will just be in terms of h. Right, so let me go to the next page and do that part, okay? Because I'm kind of, well, maybe I could squeeze it in here. Write it down here at the bottom. So we'd have volume equals 1/3 pi. In place of x squared, I have that 100 minus h squared, and that's times another h. Now, yes, I'm going to want to distribute all that before I do anything. Because remember, I'm probably going to end up using like first or second derivative. I know when I did this one, I did the first derivative. If you wanted to think of the domain again, well, I can't have negatives. And since my original radius was 10, I know nothing can be bigger than 10. You know, because the slant height in the cone is always going to be the longest length and dimension of the cone. So once again, I end up with something that's not a closed interval. All right, so that kind of rules out the extreme value theorem again. So I am going to have to find the first derivative, and then I can decide if I want to do first derivative test or second derivative test. All right, so let's pick up right from where I have that volume rewritten, and I'm going to go ahead and distribute that. So here, maybe I can leave that peeking right there while I do that. So when I distribute, I got 1/3 pi times 100, then times the h on the outside. So I could do that like 100 pi over 3 times h. And then I have the 1/3 pi times an h squared times another h. So that's minus pi over 3 h cubed. Now notice how everything's just in one single variable now. All right, so that's my rewritten original function. So I do need to go take the derivative now. So that's not so bad. That's just going to be 100 pi over 3 minus pi h squared. And I need to set that equal to 0 and solve it. Because remember, I need my critical numbers no matter which way I decide in the end to do this. I am going to need my critical numbers. So let's see, maybe I can kick the pi h squared over to the right. So I could cancel out pi. So I have h squared equals 100 over 3. So h is going to be, I can do square root of 100, so that's 10 over square root of 3. You can leave it that way. That's perfectly fine too. If you want to do a decimal, that's fine as well. Just remember when you're writing it down, you want to round it to thousands. I would also store this as something in my calculator. All right, I'm just going to call it h because that's what it is, the height. That's one reason a lot of people just prefer to keep the exact value of 10 over 3, root 3. All right, so that's my critical number. All right, so now I have to decide if I want to use the first derivative test or second derivative test. Well, let's first take a look at that first derivative. That's a really easy one to take a derivative of again, so maybe I'm going to go with the second derivative test. Because that's a really easy derivative to take. So if I do the second derivative, 100 pi over 3, that derivative is just nothing, it's gone. So my derivative is just simply negative 2 pi h. And then remember, that's what I want to substitute that 10 over root 3. I'm just going to write it as the exact value. So when I do that, that comes out as a negative. It's less than 0. So remember, that means that the volume is concave down. So remember, it looks like that. So that's where I get my relative maximum from. So in this case, let's see, we wanted to figure out the volume of the largest cone. All right, now remember what x stood for in our picture. X was like the base, like the radius of the base. So if we want the volume, what we probably want to go back to is this. go back here. All right, substitute in there either the value that you stored or the 10 over root 3. So you get that volume is about 403.067, and what were the units on it? Cubic centimeters. So that's the biggest cone you can make. Now, if you had preferred to do first derivative test, definitely give it a try. You'll have a number line with that 10 over root 3 on it. You can mark off your domain going from 0 to 10, just so you know, don't pick anything negative, don't pick anything over 10. In this case, it should have come out as a plus to the left and then a negative to the right, and that's what creates your relative maximum. So if you think you would have preferred the first derivative test, definitely pause this and give that a try to make sure it works for you. All right, so as promised, we're going to do one more, then call it a day for you. This is a really, really typical type of problem as well. So we have a farmer who wants to fence in 60,000 square feet of land in a rectangular plot, then divide it in half with a fence parallel to one of the pairs of sides. What are the dimensions of the plot requiring the least amount of fence? So it is a rectangular plot. Can you tell we draw a lot of rectangles? All right, and we know the area is 60,000 square feet. Now he wants to divide it in half. Now the big question becomes, which way do you want to divide it in half? Yes, you could really either go up or down or across. It does not matter. I'm going to do up and down. So I'm just going to put it right here. I'll do it in a different color. Okay. So I need to label my diagram. So let's call the up and down heights, let's call them Y. We'll be really creative. And I'm going to call going like all the way across X. And the same would be, of course, true on the top. So what we're trying to do in this case is we want the dimensions of the plot that will require the least amount of fence. Well, you have to think about where the fence is going to go. All right, anything that's a black solid line is going to be a fence. So here's going to be fence. Here's going to be a fence. Here's going to be a fence. Here's going to be a fence. But also the one in the middle. All right, so you need to write an equation to express that. Well, first of all, you need a variable. I'm going to be really creative again and use F for fence. So I want to minimize this kind because I want the dimensions that are going to require the least amount of fence. So I want to minimize amount of fence. F. All right, so it's kind of sort of like perimeter if you think about it. So I got 3 Y's and I got 2 X's. So that's my primary equation. That's what I'm trying to minimize. As we saw in the last example though, can't have 2 different variables. We cannot have both an X and a Y. So this is where we need a secondary equation. This is where the area comes in. All right, because remember we knew our area was 60,000. So think about how you get area, length times width. So that's just going to be X times Y. Now you can decide which variable you want to solve for. It really doesn't matter. I'm going to solve for Y just because that's how I have it written out. So I'm going to have 60,000 over X is equal to Y. And I'm going to put that in there. All right, that will allow everything to be now in terms of X. Okay, so let me write out what that would look like. Let's see if I can kind of keep that poking out right there. All right, so what it looks like now is F equals 3. And then this is where I'm putting in the 60,000 over x plus 2x, sorry. So that gives me 3 times 60,000, that's 180,000 over x. I could think of that as x to the negative 1 because remember my next step is going to be finding the derivative. So you might find it easier to bring that x up. Let's talk a second about the domain. All right, because we know that if we want to use either the first or the second derivative test, we're going to need that first derivative. Okay, so we know what to do there. But let's kind of think about the extreme value theorem, which we still haven't been able to use yet. Well, the domain for, well, we know we can't have negative values. We know that much. And we're assuming we're talking about, once we have everything in terms of x's, once we make that substitution from the area equation. We know we can't have negatives, so we know it has to be bigger than 0. Can't equal 0, because then you don't have a length. So that just doesn't make sense. The question, you don't really know how high it can go, though. That's the big unknown. So this ends up actually being like a domain of 0 to infinity. They don't really tell you, because there's lots of different combinations of numbers that will multiply to give you 60,000. So, I guess none of them can be over 60,000. Well, I guess they could be because you could have a half times like 120,000. So, you really don't know how high you can go. So this is one where the domain ends up being 0 to infinity. And again, that's something you're going to see a lot of. All right, so I think we're sticking to either the first or the second derivative test. So let's go ahead and find our derivative. So we have 180,000 times the negative 1, so that's negative 180,000. It would be x to the negative second, so I'm just going to throw that down to the denominator. And then plus 2, and remember we need to set that equal to 0. So let's go ahead and try to solve that. I'm going to kick this negative 1 over. So I'm going to keep the 2 there. And I can go ahead and cross multiply just like we did before. So if you solve that all out, let's see, you get 180,000 divided by 2, that's going to be 90,000. So x ends up being 300. Feel free to check it on your calculator. So that's our critical number. Remember, we would technically consider where the derivative does not exist. Of course, that would be at 0, which we know we can't equal anyway. So we'll just go with the 300. So once again, you have a choice at this point. You can either do the first derivative test or the second derivative test. I'm going to do the first derivative test just because I don't feel like dealing with that x to the negative second that I would have. So I'm just going to do first derivative test. And that's what I mean. My hope for you is that you'll become flexible enough that you can kind of do what I just did. Kind of look at it and say, you know what, I don't feel like doing a second derivative on that. I'm just going to do a number line in first derivative test. That's what I'm hoping you can get to for yourself. So we're going to have a number line with 300 on it. We know we can't go below 0, so just kind of keep that in mind. Make sure you're indicating you are substituting into your derivative. So that derivative equaled 0 at 300. So we want to first pick something in between 0 and 300. And you're substituting into your derivative. So like right here. Okay. That gives you negative to the left. And then if you pick something just a little bit bigger than 300, you get a positive over here. So what happens is our first derivative is changing negative to positive. That means our original is changing from decreasing to increasing, therefore creating a relative minimum. So what we end up with is that to minimize the amount of fence, the plot should be, so the 300, remember that was an X, which was going across. So 300, is it feet, I think, long. Okay, so going across. And then to figure out the Y, easiest place to go back to your secondary equation. That is always the easiest place to go to get the other variable. So then you're just doing 60,000 divided by 300, you get 200. So that tells us like how wide, like up and down, the field should be. So you can see for some of these you do actually have written answers, kind of like we had for related rates. Okay. So, that being said, I'd like for you to try some of these on your own. Like I said, I'm not going to give you too many. I'm going to hand pick which ones they are. So for homework, this is in our text. It starts on page 283. Might go over to 286. Number 2 is similar to one that you saw in the video. You're trying to find two different numbers that meet a certain criteria. It might have been the first video, like that one. Okay, so maybe you want to go back and watch that first video again before you tackle number 2. But they actually ask you to make like a table of values to kind of figure it out the old-fashioned way, like you might have in grade school, but then actually do it with the calculus. Okay, so that's number 2. Number 4 is going to be a fence problem, like this one we just did. Okay, feel free to use F for the amount of fence. I think you're trying to maximize area in that case, though. Okay, and I want to try to stick to ones that kind of look like the one, and we didn't do cost, so I don't want to give you one of those yet. Let's do 20. That's a volume one. 20 is volume of a box. Okay, so just try those 3. That's it. We will definitely go over them together. Okay, hopefully I'll see you soon. Remember, knowing that you do not have class on Wednesday the 29th, which is the day you will be watching this, remember your quiz is supposed to be today. So if by chance you have class tomorrow, school tomorrow, remember you'll be doing your quiz. Okay, but I'll be in touch by email. Okay, so if you have any questions, just shoot me an email. Okay, I'll be checking all day long. Otherwise, if you could work on these, that would really be a big help so we can kind of keep on track, because I don't want you to lose out on time at the end to review for either our final exam or for the AP exam. That's why I have to kind of keep pushing you, okay? So thank you for doing this on your snow day off. I do appreciate it. Please know that. All right, but try to have fun sometime during the day, especially if you can go out and play in the snow. But be careful. Some of you are not used to playing out in the snow. So be careful, okay? But go ahead and get this stuff done, and I'll be in touch and talk to you soon. Thanks again.